Okay, so let's go into the details of these of this particle system here, and what we're going to do is we're going to break down this entire system by its class, and we're going to work from the end back to the beginning. And the reason being is that so what that means is we have the world main class, we have the emitter class, and we have the particle class. But because of the way things work, the main requires emitters to do its job. But the emitter can't do its job until it has particles. So since they all rely on one another and there's kind of like a chain, we know that everything is going to basically require the particle. So we're going to start with particle and then work our way backwards back up to the main eventually. You're going to find that based on the last video, I've actually had to add a few things here and there, which I will discuss in this video, just to account for the fact that XNA has some differences in it versus Java, which is part of the other discussion that I'm doing simultaneously with these videos. In any case, so we're going to start by looking at the code, and we're going to look at the particle class. What I want to emphasize is that basically the particle is nothing more than a projectile. You need to remember that. So all the same stuff, if you went through the projectile videos and demos and whatnot previously, then you'll see a lot of similarities here. So we're going to follow the exact same roadmap of how a projectile flies using this code as well. We're going to take into consideration things like time passed since the last update and all that kind of fun stuff. So let's get right into it and see how this works. So basically, let's look at the data first. And the first thing you'll notice is that almost all of the data is basic projectile data, because that's all the particle is. It's a projectile. Is it currently launched? Great. What is its gravity applied? What is its wind applied? What angle is it being launched at? What speed is it being launched at? What is its image? Where is it drawn? What transparency level should I draw it at? Now this start transparency, start position, start trajectory, and start forces, these are duplicate data. And the reason why this exists is for when we recycle particles after their time has expired, we want to reset them back to the calculations that we've already calculated. We don't want to have to recalculate things if we can avoid it, because it's a very expensive thing, especially when you're talking about thousands of particles. So we want to reduce that extra CPU work as much as possible. So we're going to try and reset it when applicable. You're going to find some points that's not always the best option though. So anyways, we have our position vector, our trajectory, and our forces. So this is an accurate representation of where the particle is currently on the screen. And this will take into consideration partial pixels, which we can't actually draw. But what it'll do is it'll kind of average itself out over time, like 1.2, 1.8. It's still 1 when we cast it down to an integer. But then it gets eventually up to 2, and what's going to happen is it's going to be a nice smooth motion when we actually see it visually with our eyes. Trajectory represents the path that it's going to follow. Now this is calculated based on the angle and the speed using some basic trigonometry, which we'll get into in a second. Forces, these are the opposing forces that are applied to the trajectory every single update. So gravity and wind and that kind of stuff, and that's going to basically reduce the trajectory to eventually make it come down towards the ground again, creating that nice perfect parabola. And again, then we have our duplicate data. Below this we have our collision data. Should it collide with walls? True or false? Screen bounds. What are the boundaries of the screen? So what you'll notice here is I've actually set up a whole bunch of default data. This is not necessarily going to be used. It's just there for good style to make sure that there's no problems when we compile and everything like that. So when we get into the particle data, and what you'll notice is that there's only really two pieces of particle data: lifespan and life spent. Other than that, it's just a basic projectile. There's no differences. So what lifespan is what is the full amount of life that this particle is going to exist for. Now this is measured in milliseconds. So like 2,500 is 2.5 seconds, because there's 1,000 milliseconds in a second. Life spent is how much of that time has been used up. So for example, if the lifespan is 2,500 milliseconds, life spent starts at 0, and every update a certain number of milliseconds are going to pass since the last update. And we just keep a cumulative total of this, and eventually life spent is going to get to lifespan and the particle is going to die. And if it's a cycling particle system, it will get recycled. If not, it just dies. And then down here I just have a random number generator. You'll notice that I'm not initializing it saying equals new random, and the reason why I'm doing that is because we do that in the main and we only do it once per program. And then we're just going to pass that around. If we have multiple versions of random, what you're going to see is like all the particles going along in the exact same path, and it doesn't actually give us any randomness because it's the way that it seeds is kind of awkward and it creates problems. So if we have one random object per the entire program, we are actually going to get something much more akin to true randomness, as far as true randomness exists in reality, which is not very far. So anyways, let's get to the constructor of our particle system. So our particle is made up of a lot of different components. All of this component is data that's given in the parameters. What you'll notice is that the parameters, there's a lot fewer parameters than are actually variables up here, because a lot of this data up here is actually calculated. It's not passed in. So for example, new image represents the particle image. We have the destination rectangle where it's being drawn, how much gravity is being applied, how much wind is being applied, what is the angle it's being launched at, what is the speed it's being launched at, how long is its lifespan, what is its transparency level when we first start. Here we duplicate that transparency level into start transparency. Is it collidable with walls? And what are the screen boundaries for the game world? Duplicate the random number generator, or copy the random number generator so we have it, so we can use it for later on. And then now we do some magic here. So our start position is where are we going to currently launch our projectile from, and this is based on the destination rectangle which we set up above here. Where is it being launched from? X and Y. Now we're just storing this so we can reuse it later on when we recycle our particle. Start trajectory. Now this is where we get into some trigonometry. I'm going to go into more detail in a second, but basically we just follow some basic SOHCAHTOA. We create a triangle where the speed is the hypotenuse of the triangle and the angle is the angle at which that hypotenuse exists at. And then we're going to calculate the x and y components, which basically is our slope, and that is our trajectory. What movement path the projectile is going to follow along. And it's going to move on that path every update by a certain amount. So that might be an x of 3 and a y of 4. And that's how much movement it will have in 1 second. So 3 pixels by 4 pixels in 1 second. Now, every update doesn't occur every 1 second. It occurs a fraction of a second, maybe every 0.016 of a second. So then we would take those x and y components and multiply it by how much time has actually passed. Since those components represent 1 second, if only 0.016 seconds passed, then we multiply the 3 by 0.016 and the 4 by 0.016, and that's how much we would actually move. Again, that goes into our highly detailed position variable, which actually can take on fractions of pixels. So then we don't actually lose anything, and it will actually move. It doesn't get reset back to 0 every update. So that's how the trajectory is calculated. Forces, now this is a very simplified version of a particle system. I need to emphasize that. With real full-on particle systems, we can do a lot more than what we're doing here. We're creating a very simplified version which you can then apply to your programs and build upon in any way you want. So our forces are going to be very simple. Gravity is going to affect the y component of the trajectory. Basically, it's pulling it down towards the ground. The wind, we're going to keep wind limited to the x component on the horizontal. So wind's either going to blow to the right or it's going to blow to the left. And that's going to, again, affect the trajectory of our particle. So if our speed is moving us towards the right, but the wind is actually stronger than our x component of our speed, the projectile is actually going to move to the left instead of the right. So think about it, if you threw a leaf into the air, but the wind was blowing in the opposite direction. It would take that leaf and send it the opposite way. It gets overcome. So anyways, so that's how we build a particle. So let's get into all the nitty-gritty. Update. First and foremost, this is the biggest change for a particle versus a projectile: lifespan. So every update, we add on how much time has passed since the last update into the life spent variable. If that life spent value is greater than or equal to the total allowable life of that particle, we kill the particle. We reset it back to its launch position, and we return false. We have to tell the emitter that the particle is dead. And the emitter needs this information to decide whether it should recycle it and launch it again, or whether it should just leave it dead or not. So we return false to indicate that it is dead. If this occurs, then none of this code below it even executes, because return immediately ends the subprogram. However, if it doesn't get into this code and it should be updated, it calls the update projectile code. And this just moves it along the trajectory, taking into account the opposing forces like gravity and wind, and that's it. And then below that, we have handle any collision detection. In this case, all we're doing collision detection potentially is with walls. So if it hits the left wall or the right wall, it's just going to reverse the X trajectory. If it hits the top wall, it's going to reverse the Y trajectory. If it hits the bottom wall, it's also going to reverse the Y trajectory, making it bounce up. But I've actually added a little bit of extra here that reduces its speed, its trajectory, just to simulate the idea of it losing energy when it bounces on the floor. You could do the same thing with the walls and the ceiling as well. It's up to you. I've just done it with the floor just to kind of give it a bit of a realism when it bounces off the floor. Like if you drop a ball on the ground, it doesn't bounce to the same height that you dropped it from. Of course not, right? It loses some energy during that impact with the floor, some kinetic energy. So if the particle is not dead, then we return true, saying, "Hey, I'm still alive. Keep going, please." So draw just basically just draws it and multiplies by the transparency to give us the actual transparent value of the image itself. Nothing special there. Is active just returns whether the particle is currently in the air or not. It's being launched. Set transparency just sets a transparency level, but it caps it between 0 and 1. This is to make sure that it's actually a valid value, and I just do that using some simple minimum and maximum. I say give it the minimum value of 1 and whatever the transparency is, and the maximum value of 0 and whatever the transparency it is. So it just keeps it bound between that value of 0 and 1. We could separate this into separate commands, but I'm lazy, so yeah. Anyways, get transparency just returns the current transparency level of the particle. Get lifespan returns the maximum amount of life that particle is going to live for. Get life spent returns how much of that life has actually been spent. Now the reason why we do this is so we can do other effects. So imagine that 1,000 milliseconds have been used up of a 2,000 millisecond lifespan. That means half of its life is gone. Well, then you could take this information and you could apply it in certain ways. So maybe you want it to start fading out, like going more transparent as it dies. So it creates like a simulation of it fading out of existence. So basically you would just take its current life percentage, let's say 50% of its life is still remaining, and set that to the transparency level, and all of a sudden you have an image that's fading out, and every time you recalculate this, you just make it fade more and more and more each time. So you can create some pretty cool effects. You could do other things as well, such as like manipulating the images itself, but that's up to you. So how do we launch our particle? Very easy. We just set it to active. That's it. That's all there is to it. If it's not currently active, set it to active. Return true saying, yep, we set it to active. However, if it's already active, we return false saying, what are you doing, man? It's already done. Go on. So reset particle does exactly what you think it would do. It would take the particle after it's dead and put it back to its launch position. It would reset its current trajectory back to the original trajectory that we already calculated and did the math for. And same thing with the forces. Resets it back to the original wind and gravity forces. And then it sets the destination rectangle back to the original position, so it's where we expect it to be. Resets how much life has passed, because we don't want any of it to pass yet, and it resets its transparency so it goes back to the way it was initially. And then it says deactivate, so it will no longer be updated and it will no longer be drawn, because as you can see here in both update and draw, it checks to see whether it's active before it actually does any of that work. So then we get into Calc launch trajectory and set force vector. Now this is where the math comes in that I was telling you about before. The Calc launch trajectory just does some simple trigonometry. It says give me the angle in radians, not in degrees. Take the cosine of that angle and multiply it by the speed. If you do the math, basically that is just doing the co part of SOHCAHTOA again using speed as our hypotenuse, and the angle being the angle of the triangle. And then the y component, because y increases as we go down, we're going to take the negative value of the y component, not the positive. And we're doing the same thing, but this time it's sine. So just draw it out. If you're having trouble visualizing this, let me just see if I can quickly draw it out for you here. And basically what's happening is, where's my pen? Here we go. Basically what's happening is we launch at a certain speed, and we launch at a certain angle, theta. And then what we want is we want the x and the y components, which represent the slope of our trajectory. So every update we're going to move by x pixels and y pixels. But we're going to multiply that by how much time has actually passed, because if it's not a full second, it's actually going to be, it might be something like, 3 multiplied by 0.016, which is far less than 3. And then that value would then be put into position.x. Okay? And then it's added into position.x, I should say, not assigned to it. And same thing for, similarly speaking, for the y. So this trigonometry here, we use SOHCAHTOA. So we're going to use cosine and sine. Okay? So that is our trigonometry lesson of the day. And then we get into set force vector, and this is very simple because our wind is representing our horizontal. We're just going to set that as the x component, and gravity represents our vertical. We're going to set that as the y component. Alright. Whew, this is a long video. Sorry about that. Update projectile. So this is where all the math happens in terms of moving it. So here's the basics of it. We have to calculate how much time has passed. Now we're given time in the form of milliseconds, but everything else is in the unit of seconds, so we have to kind of factor it down. So we're going to take our milliseconds, multiply it by 0.001, since there's 1,000 milliseconds in a second, and that will give us how much of an actual second passes. So for example, if 12 milliseconds pass, that's 0.012 seconds. So that's the number we're going to be using to scale up all of our values. So add vectors and scale vector, that's the add vector just adds two vectors together, the x component with the x component, the y component with the y component, and scale vector multiplies the x component and the y component by a value, which is what I was mentioning before. So the x by the time and the y by the time. And that's how we calculate the trajectory. So and this is done on a permanent change, so that the trajectory is actually being modified here. So we're scaling in the opposing forces, the gravity and the wind, onto the trajectory, and then that's how it's being modified. So basically every update, that gravity is going to slowly pull that vector down to eventually point down towards the ground. And anyways, so then we update the position. Again, we're going to add to the position the current trajectory.x multiplied by the time passed, because again it is a scaled value. And then finally, once we have that super accurate position, we then cast it to an integer to get rid of all decimal places, and then store that in the actual destination. So again, we might have like 1.2, and then the next update 1.5, and the next update 1.8. Those are all a 1 as far as the destination is concerned. And then finally, it might cross the 2, and then that destination now becomes a 2. So that's how update projectile works. It'll physically move through the air in a nice parabolic curve until we tell it to stop, which is where projectile collision comes into play. Whenever it hits a wall, we just reverse its trajectory depending on what wall it hit, and we also adjust it so because based on the speed of that projectile, it might actually exceed the wall boundary. So we're going to kind of shift it back so it's directly in line with that wall boundary, which is what this does every time when we're adjusting the position in the destination rectangle. And then you'll notice for the floor, this is where I've actually scaled things in. So I inverted the y trajectory, but then I actually scaled the trajectory by a random number between 0.2 and 0.4. The RNG.next doesn't give us decimals, so I just did a random number divided between 2 and 4 and then divided that by 10 So it would either be a 0.2, 0.3, or 0.4, or something along those lines, or some 0.25, whatever. And then that gives us a little bit more accurate representation. So it's actually reducing the trajectory by quite a bit here. So that is our projectile collision, and then we get into randomized trajectory, which is really the last main thing. And basically this just re-randomizes our ranges of speed, low and high, and our low angle and high angle. And the reason why this exists, the emitter will actually call this typically, and it'll say, hey, when you reset this particle, I want you to re-randomize its trajectory. And the reason being is that will allow us to create a little chaos. So let's say, for example, you had a particle system that was only shooting out like 5 particles. The problem is if that system is cycling and you're just resetting them and using the same trajectory and the same trajectory every single time, it's going to start to develop a pattern, and people are going to notice this pattern. It's going to look pretty ugly. So by re-randomizing the trajectory every single time, or however often, you actually create a bit of chaos, and that chaos will produce a much cooler effect, much more realistic. And then finally, I just have 3 simple subprograms down here to manipulate vectors. Copy a vector, scale a vector, and add 2 vectors together. And that's our particle class. Everything you should need to know there. Hopefully it's all clear, and if you have any questions, of course, you can always contact me, depending on how you're watching this video. Okay, next update, or next video module, we're going to look at the emitter, which should be a lot shorter and a lot more simplified, because it's just going to be basically creating those particles. Alright, thanks for listening.